Equations with square roots. The test sometimes gives us an equation to solve involving the square root. In such an equation, the variable will appear under the radical. So, for example, this would be an equation with square roots. Square root of x plus 3 equals x minus 3. We'll solve this one later in the video. So this is the type of equation we'll be talking about in this lesson. Certainly, we undo a square root by squaring, and we are always allowed to square both sides. Sometimes with the simplest radical equations, all we have to do is square both sides. So for example, if we had something like square root of x plus 2 equals 3, well, just square both sides. We get x plus 2 on the left, we get 9 on the right, subtract, and we get x equals 7. Fantastic. But that equation was a bit too simple to appear on the test. The test is not actually going to hand us something simple on a silver platter like that. It's going to be a little trickier. Before we go on, let's think about this. Is it always true for any value of k that if we take the square root of k squared, that we'll get back to k? That is to say that the square root undoes the squaring and always takes us right back to where we started from. Is that always true? And of course the answer is no. The equation is true for positive numbers and for 0, but not for negative values of k. For example, if k equals negative 4, then of course when we square it, we'll get positive 16. Negative 4 squared is positive 16. And when we take a square root of 16, we get 4. In other words, we don't go back to the original starting number. So that's important. This suggests we may run into some kinds of problems when negative values arise. So this is on our radar. What happens when we get negative values, in particular when the thing under the radical is negative? We have to pay attention to this. It turns out that in radical equations we have to be aware of extraneous roots. When we do all of our algebra correctly, including squaring both sides of the equation, the algebra can lead to answers that don't actually work in the original equation. These are extraneous roots. So I want to emphasize this is not about making a mistake. In other words, even if we do all the algebra correctly, just by virtue of the fact that we square, we produce extra roots, extraneous roots that are not ones that actually solve the original equation. It's important to understand extraneous roots will arise in a radical equation even if you do all the algebra correctly. Now we can look at the equation we had at the beginning. So here's the equation from the beginning. So of course what we'll do is we'll square both sides. Of course that binomial squared on the right side, we FOIL that out to x squared minus 6x plus 9. You may remember the pattern for the square of a difference. Then we'll gather everything on one side, so we get a quadratic equal to 0. We'll factor that. It's very easy to factor. And we get two roots, 1 and 6. Now normally with algebra you'd think, okay, we must be done. We found the value of x. But with radical equations we have to be careful. Do we know that both of these roots work? Maybe they both do, or maybe one of them is an extraneous root. So we have to check our answers. We have to check each answer we found to make sure they work. Because right now, just looking at them, 1 and 6, we don't know. Are those both true roots? Are they both extraneous roots? Do they work in the original equation? The only way we find out is by plugging them in. So here's the original equation. Here are the roots that we found from the algebra. So first of all, we're going to check the first one, x equals 1. Plug it into the left side. We get square root of 1 plus 3, square root of 4, which is 2. Plug it into the right side. We get 1 minus 3, which is negative 2. So the two sides of the equation are not equal. One side equals 2, one side equals negative 2. So this root doesn't work. Now we'll check the other one. Plug it into the left side. We get square root of 6 plus 3, of course that's 9. Square root of 9 is 3. On the other side we get 6 minus 3, which is also 3. The two sides work. So that one does legitimately work, and it does solve the problem. So this equation has one solution that works, x equals 6. That is the only solution that works. X equals 1 is an extraneous root, because even though we followed the algebra correctly, and even though the algebra gave us that root does not actually work in the original equation. We need to square both sides to undo the radical, but this very act can produce extraneous roots. If we get a quadratic after squaring, which is common on the test, the algebra will lead to two roots. Sometimes both roots work. Sometimes one root works and one is extraneous. Sometimes both are extraneous and the equation has no solution. So here's a practice problem. Pause the video and then we'll talk about this. Okay, so here we have a radical on both sides. Radical equals radical. So of course we're just going to square both sides. We get 2x minus 2 equals x minus 4. Well, very easy equation to solve. And we get x equals negative 2. All right, very good. But now, what happens here if we plug this back into the original equation? When we plug this in, this results in the square root of a negative on both sides. So we get the square root of negative 6. And square root of negative 6 is something outside the real number system. It does not live anywhere on the number line. So we can't do math with that. That is just, for our purposes, that is just an error. And this equation has no solution. Finally, keep in mind that we should square both sides only when the radical is by itself on one side of the equation. If the radical appears with other terms on one side, we'll have to isolate the radical on one side before it would make sense to square both sides. So here's a practice problem. Pause the video and then we'll talk about this. Okay, so we do not have the radical by itself. So the very first thing we have to do is subtract that 2 from both sides. So we get the radical, 4 minus 3x equals x minus 2. Now we can square both sides. And of course we get the square of the difference, the square of that binomial, and that expands out to x squared minus 4x plus 4. Now we're going to subtract 4 from both sides and add 3x to both sides, and this will lead us to x squared minus x. Very easy to factor that. That factors to x times x minus 1, and the algebra leads us to the solutions x equals 0 and x equals 1. Now we need to check these answers. Okay, so those are the roots that the algebra found for us. First of all, check x equals 0. Plug this into the left side, and what we get is 2 plus root 4, which is 2 plus 2, which is 4. Plug it into the right side, it's 0, and of course 4 does not equal 0, so this one does not work. So this would be an extraneous root. Now check x equals 1. Plug this into the left side, we get 2 plus 4 minus 3 times 1, so 4 minus 3, and of course that would be 1, and so that's going to be 2 plus 1, which is 3, and of course this does not equal 1. Does not equal the x, which is 1, on the other side of the equation. So this one doesn't work either. And so neither one of the roots that the algebra gave us works. So this equation simply has no solution. Both the solutions that the algebra gave were extraneous roots. In summary, to undo a radical in an equation, we need to square both sides. We have to move something else to the other side sometimes to isolate the radical before squaring. In other words, we need the radical by itself. So if there are other terms on that side with the radical, we need to get rid of them, move them to the other side before we can square. And the very act of squaring produces extraneous roots, therefore we must check each answer the algebra gives us back in the original equation. Fractional exponents. In this lesson, we can make explicit the link between roots and exponents. So far, the only exponents we have considered have been integers, either positive, negative, or 0. So we've been sticking with integers. What happens if the exponent is not an integer, but a fraction? What happens then? So let's explore this. For example, what would it mean to say 2 to the power of 1/2? Well, gee, let's think about this. We could do mathematical operations if we have another side to that equation. So just let's create a dummy variable, k. We'll call the output k. 2 to the 1/2 equals k. Well, notice that if we multiply 1/2 by 2, we get a whole number. And of course, we could use that multiplying exponent rule if we raise 2 to the 1/2 to another power. So I'm going to say, why don't we square both sides? Well, on one side we get k squared. On the other side, we get 2 to the 1/2 squared. And of course, the laws of exponents say we multiply those exponents. 1/2 times 2 equals 1. So that side just becomes ordinary 2. K squared equals 2. Well, of course, we can solve this for k very easily. Take a square root. K equals the square root of 2. And that must be what k equals. So in other words, 2 to the 1/2 equals the square root of 2. Raising something to the power of 1/2 is the same as finding the positive square root of it. That's important fact number 1. Now, what would it mean to say 2 to the 1/3? Well, you might guess, but we'll follow this same process. Again, fill in a dummy variable, k. And now notice that if we multiply 1/3 times 3, we'll get a whole number. So we'll cube both sides. And of course, the right side just becomes k cubed. The left side, 2 to the 1/3 to the 3. Well, the 1/3 and the 3 get multiplied, and that just equals 1, so it's 2 to the 1, or ordinary 2. So k cubed equals 2. We can take the cube root of both sides. K equals the cube root of 2. So in other words, 2 to the 1/3 equals the cube root of 2. Well, you might see a general pattern emerging here. In other words, if we take something to the 1/2, it's the square root. If we take something to the 1/3, it's the cube root. You might guess if we take it to the 1/4, it's the 4th root, 1/5, it's the 5th root, that sort of thing. And in fact, we can generalize by saying b to the power of 1 over m is the mth root of b. So this is the explicit link between fractional exponents and roots. So for example, if we had something like 6 to the power of 1/7, what that would mean is the 7th root of 6. What exactly does that mean, the 7th root of 6? This is the number which, when raised to the 7th power, equals 6. What happens if the exponent is a fraction that has a number other than 1 in the numerator? So far, we've been looking only at fractions that have 1 in the numerator. What would happen if we had something like 2 to the 3/5? Well, remember, we can write 3/5 as either 3 times 1/5 or 1/5 times 3. We can write, of course, we can write the product either way, and this has implications for the laws of exponents. I can write it as 3 times 1/5, have the power of 3 inside, and have the 1/5 outside, and so that would be the 5th root of 2 cubed, or the 5th root of 8. That would be one way I could do it. Another way I could do it would be to write the 5th on the inside. So on the inside, I have just the 5th root of ordinary 2, and on the outside, I'm cubing it. Either one of those is perfectly fine. And I will say, if you actually have to do a calculation, if you have to actually choose between these two, always make things smaller before you make things bigger. That's a very important point of strategy. Here's a practice problem where you can apply some of this. Pause the video and then we'll talk about this. Okay, 8 to the 4/3. Well, we could write that either as the cube root of 8 to the 4th, or the cube root of 8, that whole thing, to the power of 4. We could write it either way. Now the question is, which would be a better way to calculate? Well, with that first one, the first thing we'd have to do is figure out 8 to the power of 4. Well, that's going to be a large number. Of course, 8 to the power of 4 is going to be 8 squared squared, so that would be 64 squared. I don't know 64 squared off the top of my head, but that's going to be a very large number, and then we're going to try and take a cube root of it. That sounds doubtful. Whereas with the other one, all we have to do is take a cube root of 8. We can do that and then raise it to the 4th. So that first one is just a horrible idea. Don't raise it to some high power and then try to find a root. Find the root first. That's an enormous point of strategy. So we'll find the root first, and of course the cube root of 8 is just 2. So we get 2 to the 4th, and that's 16. So these rules that we've talked about are rules that are true for positive numbers, when b is a positive number. Technically, they are true of 0, though the roots of 0 are an unlikely topic on the test. If the denominator of the exponent fraction is odd, then the base can be negative as well. Remember that we could not take even roots of negative numbers, but we could take odd roots of negative numbers. For example, the cube root or the 5th root of a negative number. In summary, roots are represented by fractional exponents. That's the big idea. The square root of a quantity equals that quantity to the power of 1/2. That is by far the most common fractional exponent you'll see on the exam. The power b to the 1 over n means the nth root of b, and the power b to the m over n can be written either as the root of the power or as the root to the exponent m. Exponential equations. An exponential equation is one in which the variables are in the exponents. Most exponential equations require advanced math to solve and would not appear on the test. The test would only give us equations that could be solved using the basic laws of exponents and roots we have discussed in this module. So for example, 2 to the x equals 16. That's an extremely easy exponential equation. This is much easier than you would see on the test. And of course we can solve this when we recognize that 16 is a power of 2. So we'll just write 16 as 2 to the 4th, and then we can set the exponents equal on both sides because the bases are equal on both sides. If you see an exponential equation on the test, most likely they will have variables in the exponents on each side of the equation. So what we have there, variables on one side and just a constant on the other side, you probably will not see that. Nevertheless, the insight on the last problem can be broadly generalized. If two powers with the same base are equal, then the exponents must be equal. So if b to the x equals b to the y, it must be true that x equals y. So this is the fundamental idea that we will be using to solve exponential equations. This rule works for all bases other than 0 or plus or minus 1, and the test is not going to give you an exponential equation with one of those numbers as the base. Here's a practice question. Pause the video and then we'll talk about this. Okay, so those bases are already equal. We have a base of 7 on both sides of the equation. All we have to do is set the exponents equal and then solve. We'll add x to both sides, divide by 3, we get x equals 2. It's good to understand that problem, but still, this is easier than what the test is going to expect you to know about exponential equations. The test will never hand you an exponential equation in which the two bases are already equal. You see, in that last problem, it kind of handed us that on a silver platter. The real test problems are not going to do that. They will always give you two different bases on the different sides of the equation. Of course, we can't apply the same slick rule if the two bases are not the same, but the test will always give us two bases so that we could change one or both base to make the bases the same on both sides. So what do I mean by this? Let's go back to that last problem, but present it as the test might present it. They might give you something more like this. If 49 to the x equals 7 to the 6 minus x, then solve for x. So notice that the two bases on each side of the equation, they are no longer equal. We have two different bases. But of course, this still isn't that bad. We just have to recognize, of course, that 49 can be expressed as a power of 7. So I'm going to start with that equation, and I'm going to replace that 49 with 7 squared. And of course, I can multiply through the exponent, and now this looks like the actual problem we already solved. So in other words, just by doing that one substitution, we're able to make the bases equal. Now we can set the exponents equal and solve. Here's another along these lines. Pause the video and work on this. Of course, we have to rewrite that root as a fractional exponent, as we learned in the previous lesson. So the fifth root of 3, we have to rewrite that as 3 to the power of 1/5. Now we'll multiply the exponents. Now we have equal bases, so we'll just set the exponents equal, multiply by 5, and then just do ordinary algebra to solve. Sometimes neither of the bases can be written as a power of the other. Instead, both bases can be written as a power of some other smaller number. This is actually the most common scenario in the test. By far, the vast majority of exponential equations on the test are precisely this form. Two bases, and neither one can be written easily as a power of the other, but both can be written as powers of a third number. For example, if we had some power of 8 and some power of 16, we can't write 16 as a power of 8, we can't write 8 as a power of 16. We would have to begin by recognizing that both 8 and 16 can be rewritten as powers of 2. So we'd have to rewrite each base as a power of a common smaller number, and then by using the laws of exponents, we can get everything to equal bases and set the exponents equal. Here's a practice problem along these lines. So this now is a problem as it might appear on the test. Pause the video and then we'll talk about this. Okay, well, 27 and 81, we can't write 27 as a power of 81 or 81 as a power of 27. The first step is to recognize that both 27 and 81 are powers of 3. And we can rewrite them as powers of 3. 27 is 3 to the 3rd. 81 is 3 to the 4th. So we're just going to rewrite the equation in terms of powers of 3, multiply the exponents on both sides. Well, now we have equal bases. Because the bases are now equal, we can set the exponents equal. And now this just becomes ordinary algebra. We'll distribute. And we get 2x equals 10, divide by 2, x equals 5. And this is the answer. To solve exponential equations, we have to get equal bases on both sides. This may involve expressing the given bases as powers of smaller bases. Once the bases on both sides are equal, we can equate the exponents and solve. Now we can talk about the very important topic of rationalizing. So throughout this module, we have seen a few fractions involving radicals. Notice that so far, no final answer has involved a radical in the denominator. And in fact, I have crafted every fraction to make sure that this never happened, that it never was a result, that a radical was left over in a denominator. Now, why would I do that? This is a tricky issue. Having a radical in the denominator is considered, quote, in poor taste in mathematics. Now, why would mathematicians think this? One way to think about it is, if there are multiple fractions that need to be added or subtracted, it's helpful if all the denominators are integers so that we can find a common denominator. A more general way to say it is, if there are multiple ways to write an answer, it's helpful if there's an established convention so that everyone writes the answer the same way. And that makes it much easier to compare whether two different people have found the same answer. So for whatever reason, the mathematical convention is to avoid radicals in the denominator. Now, if a radical appears in the denominator as part of the problem, and of course it sometimes happens, we need to change the fraction to an equivalent form so that no radical appears in the denominator. This process of change is called rationalizing the denominator. That is to say, making the denominator a rational number, an integer, rather than an irrational square root. So, suppose in the course of solving a problem we found x equals 12 divided by root 3. Let's pretend that we did all the math correctly. We got this as our correct answer. This is our solution to the problem. That might be mathematically correct, but because it's not rationalized, we won't find it among the answers listed in this. We won't find the answer listed in that particular form. You see, all the answers on the test are rationalized. So we need to rationalize anything that we find to match it to the answer choice. If there's a single radical in the denominator, we rationalize simply by multiplying by that radical over itself. So we're just going to multiply by the square root of 3 over the square root of 3. And of course, in the denominator, we get root 3 times root 3. Well, think about this. Root 3 is the number which, when we square it, we get 3. So here we're multiplying it by itself, so it becomes 3. Then we can cancel the 12 divided by 3. That becomes 4. We get 4 root 3. That is the rationalized form. So the answer would never be written in the form 12 divided by root 3. It would be written in the form 4 times root 3. Practice rationalizing the following. In each case, you're just going to multiply by the radical over itself and then simplify. Pause the video and then we'll talk about this. Okay, in that first one, obviously we will multiply by root 5 over root 5, and we get root 5 over 5. In the second one, we'll multiply by root 3 over root 3. We'll wind up with 2 root 3 over 3. In the third one, we'll multiply by root 21 over root 21. We get a 21 in the denominator. That allows us to cancel a factor of 7 and wind up with 2 root 21 over 3. Those are the rationalized forms. Even if there's addition or subtraction in the numerator, divided by a single root, all we have to do is multiply by the root over itself. So for example, if we had something like 4 minus root 6 over 2 root 3, really the only thing that concerns us is that root 3 in the denominator. So I'm going to multiply by root 3 over root 3. In the denominator, I get a root 3 times a root 3, which is 3. In the numerator, I distribute. That root 6 times root 3, remember that root 6 is root 2 times root 3, so we can multiply the two factors of root 3 together to get 3, and then we're just left with a root 2 left over. So what we wind up with is 4 root 3 minus 3 root 2 over 6, and that is the fully rationalized form. Things get trickier when we have addition or subtraction in the denominator. So suppose we had to simplify something like 2 divided by the quantity root 5 minus 1. Well, what we have been doing is not going to work here. You see, if we multiply this denominator by root 5 over root 5, we would have to distribute across the subtraction in the denominator. The root 5 times the root 5, that would equal 5. That would be fine. But of course, there'd also be a 1 times root 5, and that would be root 5, and our attempt to rid the denominator of radicals would not be successful. We have to make use of a different trick. So I'll say, remember the difference of two squares formula from the algebra module. P minus Q times P plus Q equals P squared minus Q squared. If this is an unfamiliar formula, I highly suggest go back to the algebra modules and watch the videos concerning this particular formula. It's one of the most widely applicable formulas in all of mathematics. So in other words, what we have here is the product of a sum and a difference as the result of squaring both terms. If P or Q, or even both of them, were radical expressions, then on the right side of the equation above, every radical expression would be squared, and there would be no radicals in the result. Very interesting. Consider any two-term expression, either addition or subtraction, in which one or more of the terms is a radical. So we might have things like this, for example. Two terms, and we're either adding or subtracting, and one or both of the terms is a radical. If we change the addition or subtraction to its opposite, we construct what is called the conjugate expression. So that first one, we have 3 minus root 7. The conjugate would be 3 plus root 7. In the second one, we have root 13 plus 2 root 11. The conjugate will be root 13 minus 2 root 11. So how is this helpful? Well, if we multiply any expression with radicals by its conjugate, one conjugate plays the role of a plus b, the other plays the role of a minus b, so that their product is the difference of the squares of the two terms, a squared minus b squared. So for example, if we had 3 minus root 7 times 3 plus root 7, well, essentially what we have here is an a minus b times an a plus b. And of course, this is going to equal a squared minus b squared. Or in other words, 3 squared minus root 7 squared. Square each one of those, and we get 9 minus 7, which is 2. So in other words, we multiplied two expressions with radicals, and we get a product without radicals. That's a really big idea. This provides a clue we need for how to rationalize a fraction with a radical expression involving addition or subtraction in the denominator. So let's go back to that one that we couldn't solve a moment ago. We had something like 2 divided by the quantity root 5 minus 1. Well, what I'm going to do is multiply the numerator and denominator by the conjugate of the denominator. To rationalize, we're going to multiply the numerator and the denominator by the conjugate of the denominator. So what we have in that denominator is root 5 minus 1. The conjugate would be root 5 plus 1. So we're going to multiply by that conjugate. Root 5 plus 1 over root 5 plus 1. Then in that denominator, we have an a minus b and an a plus b, so we'll get an a squared minus b squared in that denominator. The numerator I'm just going to leave undistributed for a moment. And so we get a root 5 squared minus 1 squared. That will be 5 minus 1, which is 4. Then I can cancel a factor of 2 in the numerator and denominator, and I get root 5 plus 1 over 2. And that is the rationalized form. Incidentally, you don't have to know this for the test, but that happens to be the golden ratio. So rationalize the following. You will need to multiply the denominator by its conjugate. So I'm going to say pause the video and try this on your own. Okay, so we have a root 7 minus root 3. And so what we're going to need to do is multiply that denominator by a root 7 plus root 3. So we have to multiply root 7 plus root 3 over root 7 plus root 3. Multiply by the same thing over itself. In the numerator, I'm not going to distribute just yet. In the denominator, I get the square of those terms, the difference of the squares, which is just 7 minus 3. 7 minus 3 is 4. And then cancel 8 divided by 4. And we get 2 times root 7 plus root 3. And that is the fully rationalized form. Now we can distribute if we want to, depending, doesn't matter. The answer could be written in either of those last two forms. Rationalize the following. You will need to multiply the denominator by its conjugate. Pause the video, work on this, and then we'll talk about it. Okay, so we have a 3 plus root 5 in the denominator, so we need to multiply that by a 3 minus root 5. So we need to multiply both the numerator and the denominator by 3 minus root 5. In the denominator, we're just going to get the difference of two squares, 3 squared minus root 5 squared. In the numerator, I'm going to have to FOIL, and so what I get is the product of the first, 4 times 3 is 12. The product of the outer, 4, so that's minus 4 root 5. The product of the inner, that's plus 6 root 5. And then the product of the last, which is 2 root 5 minus negative root 5. Well, the root 5 times the root 5 is 5. 2 times 5 is 10. So that's just minus 10. Now we'll simplify everything in the numerator and the denominator. We wind up with 2 plus 2 root 5 over 4. Everything is divisible by 2, so we can divide by a factor of 2. And we are left with 1 plus root 5 divided by 2. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we need to get x by itself, so of course we're going to divide by everything in the parentheses. We have an expression in the denominator involving addition or subtraction with a radical, so we're going to multiply by the conjugate. We have a 2 root 5 minus 3. We need to multiply that by a 2 root 5 plus 3. And so I'll multiply by that. In the numerator, I'll just leave it undistributed. In the denominator, I'm going to get 2 root 5, that thing squared, minus 3 root squared. And of course, 2 root 5 squared, as we learned from our operations with radicals a few videos ago, that's 2 squared times root 5 squared, 4 times 5, which is 20. And of course, 3 squared is 9. 20 minus 9, we get 11. We can cancel a factor of 11 in the numerator and denominator, and we're left with 5 times the quantity 2 root 5 plus 3. And that is the fully rationalized form of the answer. In summary, to eliminate roots from the denominator of a fraction, this is called rationalizing. And it's something you always have to do. The test answers, the answers that appear in multiple choice, will always be rationalized. And so we will have to rationalize to match our answers to this. If the fraction has a single root in the denominator, we rationalize simply by multiplying by that root over itself. If the denominator of the fraction contains addition or subtraction involving radical expressions, to rationalize we need to multiply by the conjugate of the denominator over itself. Working with formulas. Sometimes the test will present us with a formula, and then they'll ask about it. The formula is usually a real-world formula from science or business or other areas. The test will always give the formula and explain what the quantities in it mean. You never need to have outside knowledge of the formula or the subject area to answer the question. Typically, the test will give you the formula, then ask one of 3 question types. There are questions that will give you some numbers and ask you to solve for others. So it's actually plug in and solve. There are also questions that ask you to solve algebraically for one of the variables in the formula. And then there are proportional reasoning questions. So these are the 3 most common questions, 3 most common tasks that they will give you when they present you with a formula. Here's a plug-in number question. Pause the video and then we'll talk about this. Okay, when a car, initially moving at a speed of v, decelerates with a constant acceleration a, its minimum stopping distance d is related to v and a by the following formula. Incidentally, this question is throwing in an idea from physics that deceleration is a kind of acceleration, that the word acceleration is actually broad and it means speeding up and slowing down. That's some outside knowledge that you don't need, but that's what's going on in the terminology of the question. So if v equals 30 and a equals 10, find the stopping distance. So all we have to do is take that formula and plug in the numbers that were given. And then we're going to leave d as a variable. We're going to simply solve for that. Well, 30 squared, of course, that's 900. I'm going to divide both sides by 10. So I get 90 equals 2d, or d equals 45. And so that must be the distance. We're not given any units, so we don't have to worry about units. That's the distance, that's the answer. Second question type, solving for a variable. So it might give that same explanatory paragraph and then give us this equation and ask us to solve v squared equals 2ad for v. And of course what we're going to do is simply take a square root. So v equals the square root of 2ad. And we can assume everything is positive so we don't have to worry about the plus or minus. For example, we might have to solve h equals 1/2 gt squared plus vt for g. And again, the formula, they may or may not give us an explanation of what this formula is. So we're going to multiply all the terms by 2. Then we're going to solve that one term that has a g in it, and we're going to divide by t squared. So we could write the answer like that, or we could split up the fractions, cancel a factor of t in the second fraction, and write it like this. Either one would be correct. This is a tricky one. Solve 1 over p plus 1 over q equals 1 over f. Solve this equation for q. Pause the video and then we'll talk about this. So a very common mistake here would be to think that we could just take 1 over everything and we'd get p plus q equals f. And so that q would equal f minus p. That is 100% incorrect. We cannot do that. So the first thing we need to do is solve for 1 over q. And then on that right side, 1 over f minus 1 over p, we need to find a common denominator. We need to make this into a single fraction by finding a common denominator. So the first fraction, 1 over f, we multiply by p over p. The second fraction, 1 over p, we multiply that by f over f. We get this. We combine the fractions to a single fraction. Well, now we have a single fraction on both sides of the equation. 1 over q equals the single fraction p minus f over pf. Well, now we can take the reciprocal of both sides, and we get q equals pf over p minus f. And that is the correct answer. Now we can talk about proportional reasoning questions. We'll go back to that same formula for the stopping distance, v squared equals 2ad. Here's a typical question. If v doubles and a stays the same, then t is multiplied by what? So the question loves this kind of question where some of the quantities, they're multiplied by this, or they're multiplied by this, they're doubled, or they're halved, and then what happens to this other quantity? They love this. So how do we approach this? Here's a very easy way to approach this. Pick ridiculously easy numbers that satisfy the equation. So, for example, we could just start out by saying that everything equals 1. And we could even set the constant equal to 1. Now, why would we doesn't make sense to set 2 equal to 1. But think about what we're doing. It's like we have two different scenarios. We have an original scenario where we plug in numbers, and then a second scenario when we plug in the numbers again, and really what we're doing is we're taking a ratio of the two equations. Well, that factor of 2 is going to be the same both times, and so the 2 over 2 is just going to equal 1 when we take a ratio, and so it's easier just to set it equal to 1 right away because we're not going to have to worry about it. So here we would set v equal to 1, 2 equal to 1, a equal 1, and d equal 1. And then we'll change whatever values need to be changed and leave the quantity in the question unknown and solve for it. So for example, in this question, I will change everything to 1. I will even change that 2 to a 1 and let all three variables equal 1 for my start. That equation works. That would just be 1 squared equals 1 times 1 times 1. So that's a working equation. Now double v and leave d as an unknown. So everything else is still 1. And I get 2 squared equals 1 times d. And so, of course, what we get 2 squared is 4. We get 4 equals d, or d equals 4. So in other words, the distance is multiplied by 4 when v doubles and a stays the same. Sometimes more than one quantity changes at once. In v squared equals 2ad, if v triples and a doubles, then d is multiplied by what? So pause the video, try to do this on your own, and then we'll talk about it. Okay, set everything equal to 1 for our start. Even the 2 is going to get set equal to 1. So that equation works. Now we're going to replace the v with 3 because it triples. We're going to replace the a with 2, and we're going to leave the d as a variable. So 3 squared equals 1 times 2 times d, or in other words, 9 equals 2d, and d equals 9 over 2. So the distance is multiplied by 9 over 2, or 4.5. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so this is Newton's formula for gravitation. The test may or may not tell you that. So we get this formula, and we want to know if P triples and R doubles, F is multiplied by what? So we're going to assume everything else stays the same. So we'll start with everything equal to 1. 1 equals 1 times 1 times 1 over 1 squared. That works. Now we're going to change the P to a 3. We're going to change the R to a 2, so we get a 2 squared in the denominator. We're going to leave the F as a variable. And what we're going to get is 3/2. So the force is multiplied by 3/4 when we make these changes. Here's another practice problem. Pause the video and then we'll talk about this. So the test may or may not tell you that this is Kepler's third law of planetary motion. That doesn't really matter for solving this. So what we're going to do is set everything equal to 1 originally. 1 squared equals 1 times 1 cubed. That works. Then we're going to replace t with 5 and leave r as a variable. So 5 squared, which is 25, equals 1 times r cubed. So in other words, r cubed equals 25. R equals the cube root of 25. We might also write this as the cube root of 5 squared, or 5 to the 2/3. Any one of those could be a correct form of the answer. The test will always give you the formula and explain what you need to know about it. The test may ask you to plug in numbers and solve, or it may ask you to solve for a variable in terms of the other variables. In proportional reasoning question, it's usually easiest to make each number in the constant equal to 1 in the starting case, and then change what needs to be changed.